This is good. Okay, so I used to give these talks on the 3 R's, and now I have a new triangle, which is about vision, motor control, and language. And the point is that all 3 of these processes are interlinked with each other. The great thing about this work on visual question answering is that it has connected up vision with language. And this really needed to happen. And I want to argue that we need to go even further out and connect it to motor control. So this talk is not going to have much in the way of direct results for vision and language. The rest of you are doing a remarkably good job, so you don't need my contribution. So I'm going to try to add to the big picture here. So let's start with the really old picture, which is thinking about how intelligence developed. And it's something like 500 million years ago when animals came to the scene, and all animals have perception as well as locomotion. And the key point here is that the benefit of vision comes in only when accompanied by action. And there is a very cool example. So Gibson had this line, which is that we see in order to move and we move in order to see. But there is a very clear example of this, which is that if you don't need to move, you don't need an eye or a brain. So there is this animal called a sea squirt, which in the early stages of its life cycle can move, and it has a vision system, etc., etc. And in its last stage, it becomes stationary. It becomes like a plant. And at that point, it eats its eye, it eats its brain, and often the analogy that has been made is this is what happens to tenured professors. Okay? So now moving from 500 million years ago to 5 million years ago, considering human evolution, there are these stages where the first most important stage was bipedalism, which freed the hand for locomotion, from locomotion for manipulation, and there is a considerable evidence that the brain evolved in response to that. Then after that you have sophisticated social organization and the development of language, which is of course very important. But my key point is that while language is very important, it arose on a substrate of perception and control which had been going on for 500 million years ago. Now let's contrast this with what happened in the field of AI. So AI, let's say from the 60s and 70s, was very much in this style of symbolic processing. And this had some value because obviously the symbol for bird has nothing to do with the concept of bird or the creature, the image of the bird or whatever. So there is this disconnect which is worth realizing. But we went much too far in that direction, and thought became merely the manipulation of symbols by rules. And this has persisted to this day, and in fact, a good example would be machine translation. You have a sentence in English which you're converting to a sentence in French, and what you're doing is picking some symbols in French and using them to replace some symbols in English. And that system need to have any understanding of what a cat actually is, or what a dog actually is, what justice is about, what hunger is about, and so forth. Now, in the cognitive science literature, there was a reaction to this extreme version of the symbolic hypothesis, which was embodied cognition. And I'm not going to get into that in great detail, but I want to point out that this is orthogonal to the issue of learning and connectionism and neural networks. This is really about the idea of a body which lives in a three-dimensional world and interacts with it, and how meaning gets grounded by that. And the two stories are compatible, but they are not the same. And my job here is to push the role of embodiment here. I'm obviously fully in line with the learning paradigm. So I'll just give you one pointer, which I think is a very nice one. This is a paper from Smith and Gasser on the development of embodied cognition. 6 lessons from babies. You can just read it, but I'll read it out. The embodiment hypothesis is the idea that intelligence emerges in the interaction of an agent with an environment and as a result of sensory motor activity. And they go on to talk about various aspects of child development. So multimodality, incremental, so there is a curriculum learning aspect, there's interaction with the physical world and so forth. And I truly believe that an agenda for research in AI and specifically in vision is to try to take this sequence of development stages in children seriously and to develop AIs on that foundation. And this way we will deal with all these problems of grounding and so forth. So, here's a picture of babies. So, you can see that a baby is not a passive entity just capturing images or capturing text. Children do not acquire language by watching television. I mean, our current set of systems are based on that kind of a model, but I want to argue that this is a limited model. We will make some progress this way, but not to our end goal. Just like a lot of NLP progress was made by just looking at documents, text, but it's not going to take us all the way. And I would say even pictures and text together will not take us all the way. So let's look at this picture of children. So clearly they interact with the world, they are doing motor dabbling, they're trying things out and so forth. And so we have in some way two examples of supervision. So there is a kind of supervision where the mother says to the child, okay, that's a giraffe or that's a zebra. But there is the kind of supervision which the child produces for himself or herself by interacting with the world, playing with the world and so forth. And the question is, what kind of information can such signals provide? And I'll just take you through some of the work that we've been doing in my group on this framework. So here's an example. So suppose you perform an action like poking. You can poke a Coke bottle, you can poke a ball, but you'll get different results. From those experiments, you've learned something about the physics of Coke bottles and the physics of balls. And this is part of the concept of a Coke bottle and the concept of a ball. We cannot just associate ball and Coke bottle with symbols and not have this knowledge. Our understanding will be of an incomplete and imperfect type. Here's another example. Moving. You move around and then the images change. Right? So that's shown by this camera. The different objects change differently. Now this is related to the shape of the object, but it is delivered to us through this interaction. So with the different interactions, so touching, poking is one kind of interaction, moving in the world is another interaction. But all of these interactions, how objects transform under them, give us some information, and that information is a vital part of that object. So let's try to be a bit more precise. So how can we exploit this knowledge? So one way to think about it is that we perform an action and then we see what is the result. So there's an initial state, which is this upright Coke bottle. There's some action that we perform. The action is chosen by me, so therefore I know the parameters of that action in some internal representation. Then the output will be, well, the world will act. Something will happen, the bottle may fall down. And that's another image that I will see. So essentially I have two inputs, the image and an action, and then the output is another image which I will see. And we really want to understand this triplet, this relationship between these three variables. And you can take any, so normally you're going to be given the first two and you try to get, in order to get a desired output, but for learning we might do it in any combination we choose. So here's, the one way in which there have been lots of papers in the neural network literature have been written is to try to produce images as the output. But this is actually difficult and probably a bad idea. It's a bad idea because it's not operating at the right level of abstraction. So again, when I talk about a video stream, we all want to do prediction. But to me, prediction in the next frame or the next frame could be done by optical flow. That's trivial. If you want to go further out, that prediction should be at a more symbolic high level rather than at the level of pixels. Okay, so then we don't want to predict pictures. So what we want to do instead is to predict. We just switch this around. We take the initial image and the final image as input and try to predict the action. But we will know the action. So here's an idea. So this is you have three variables, x, y, and z, which have a relationship between them, and you can choose two of them as input and try to predict the third, right? And we can do it in any combination. So that's the basic trick. So in the case of the poking formula problem, what we could do is to take the image before and image after as inputs which go up a neural network, and we try to predict the poke location. But we executed the poke, so therefore we have an error signal we can use to try to train this network. Or for ego motion, it might be that you have a one frame which you run through your network. You have another frame, you run that through the network, and you try to predict what was the ego motion that could have caused that transformation. But you in fact know the ego motion because you did it yourself, so you have now an error signal which you can use for training. So you see that this idea can be exploited in a couple of different ways. And I'll show you a few works which have built on this theme in a more concrete way. So here's a paper from my student Pulkit, who has led this effort at ICCD. So that's what is the data set we took? So we took the Kitty data set, and this has audiometry available for the images captured from a moving car. And basically, you have an image, and then the car moves, but you know that movement. You can predict the next. There is the next frame, and so you can run it through this network that I gave you a sketch for, try to predict the camera translation and rotation. And the beauty is that we just do this in supervision. So there is no external supervision going on. It's all self-supervision. The network develops receptor fields which are very interesting. They correspond to orientation and so forth. And we can then test this network in our classical tasks like recognizing digits and so on and so forth. I'm not going to get into details here, as well as scene classification. And it does a pretty credible job. It's as good as 20,000 examples from ImageNet for use. So this tells you how self-supervision could work. Okay, so moving on. Let me now turn to the actual action task. How do we build agents that can learn to perform novel tasks in novel environments? So I'm a history buff, so I always like to find the oldest reference for some idea. So here is this paper from 1943, which really is, in a way, the beginnings of cognitive science. And from Craig, there's the same Craig O'Brien Constraint Illusion. And his basic idea was that humans have a model of the world in some simplified way with which they can do forward simulations. And this is what enables us to plan and act in the real world. Okay, so how do we acquire these models? So we went about trying to do this. So here is a billiards and a pool environment. So what do we want to do? We want to hit the ball and have certain things happening. So what we need to do is to learn physics, right? So but we learn physics by observation. So by just applying various forces and then see what happens. So this is kind of the goal. So there is an image, there's a current state, you apply a certain force, you get an actual state, and you try to match your prediction with what actually happens. And this way, again, I will not get into the usual mumbo jumbo of CNN, RSTM, blah, blah, blah. Okay? And And as a result, the model now has in its imagination basic Newtonian physics. And so here we got ground truth from physics, from real physics. We were trying to get the network to learn. We were generating these movies from real physics and using that to learn intuitive physics. And you learn very sophisticated physics, including collisions with walls and balls, etc., etc. I'm going to skip the details, and this enables us to plan actions. Okay. Then our latest work has to do with trying to do this in the real world. So here's a picture. Let me. So here we have a robot trying to do porting action. So porting implies you start in a certain direction and you push an object. And this is completely automatic. There's no human intervention required. And then there's this final stage of sweeping. So, but you put different kinds of objects in different directions, and essentially you learn physics. This is intuitive physics. This is not the same as Newtonian physics. So I'll give you an example. In Newtonian physics, a marble and a feather, they should behave the same. In real life, a marble and a feather don't behave the same. So in physics, you are taught differently. But to deal with the real world, actually Aristotelian physics is perfectly good. In fact, you need to learn it in a crude way, and that is how you can deal with the everyday world. So how do we, again, the question we for doing this is, in the initial state, final state, we come to physics the truth, and we find that here it is helpful to have a forward model and an inverse model being trained at the same time. So again, I'm going to skip the details. It's all there in an archive note, which is that you are trying to train a predictor for the action as well as a model which can, given a certain image, predict what will happen if you apply a certain action. And this gives you the wherewithal for planning. Okay, so that's basically it, and it does work. Now I want to mention that this idea is, I think it's a very new, in a way, a new idea, because it goes away from the classical robotics approach, which is that you try to think hard about the problem and model it. Essentially, the classical roboticists are doing what in computer vision was done by the physics-based vision people, which is that there is this conceit that we are scientists, we can study enough about the physics and we can model it, and then we'll have a complete way to understand the situation. Instead, here, the machine learning approaches in vision what are they doing? They're saying we do not try to capture the physics. We have lots and lots of data from which we will try to learn. So the same idea in a robotic setting is, instead of building in Newtonian physics, we are going to experiment with the real world. That generates examples which are the data for training a certain kind of network, and we can build in a fair amount of sophistication in there because we need to generalize, and that sophistication comes by understanding, modeling the environment as well as the agent. So there's work from Abhinav Gupta's group on trying to grasp from many trials. There is an ARM-Farm work which came out of Google and so on. Okay, so just to conclude, back to this big picture. Everyone in this room came expecting me or anybody else in this session to talk about vision and language, and I have bypassed that. I've talked mainly about vision with motor control. But the reason why I'm doing this is because I believe that we in the vision community have made a lot of progress. But it is not a good idea to circumscribe problems narrowly. We need to think of problems as broadly as possible. And we now have the tools in terms of computing power, data, etc., etc. So richer formulations of the problem are what will result in the biggest advances. And from that perspective, I want to suggest to you that bring in motor control as part of the story. Thank you.